Hi there, folks. Today we're looking at reasoning in algebra and geometry. We're going to get into formal proofs today. And so we're going to start with just a reminder of some of the properties from algebra when we were solving equations and doing things like that. I'm going to breeze through these pretty quickly because you should already know these. However, you might not remember all of the names. You probably know how to use each of these, but we're going to kind of classify them in terms of names when we start doing proofs. So you might have to pause this as I run through this because, again, I'm going to go through it quick. And if you need to pause and write some stuff down, that's okay. But you should be familiar with most of these things. So, algebraic properties that we've had in the past, addition property of equality, that's the one that says, hey, we're allowed to add the same thing to each side of an equation. I've got a little asterisk next to subtraction property of equality. If you want to call it subtraction property of equality when you subtract from each side, that is fine. But really, that's kind of a made-up property. It's still the addition property of equality. You're adding a negative. So if you subtract the same thing from each side, you can still call it addition property of equality. All right? Multiplication property of equality, we're allowed to multiply each side of the equation by the same thing. All right? Division property of equality, we're allowed to divide each side of the equation by the same thing. And again, technically, the division property of equality is covered under multiplication. But again, if you do the same operation to each side, say it's that operation of equality, that's the property we're looking for. Okay? And then some ones that maybe we don't remember as much. The reflexive property is basically when we say something equals itself. We don't typically use that one a lot in algebra, but that'll come up quite a bit here in geometry when we get into some of the more complicated proofs, all right? Every once in a while, you'll need to say, hey, this thing equals itself, all right? Seems silly, but it'll be important later. The symmetric property you use all the time without even thinking about it. Like if you solve an equation, you have 2 equals x, you typically rewrite it as x equals 2. That's the symmetric property. It says, hey, you can flip the thing around and it's all right, all right? The transitive property, we've already talked about this one, and we've talked about the geometry version of this when we're talking about truth tables. That was the law of syllogism. But the transitive property of A equals B, B equals C, then A equals C. It's that kind of bridging the gap from one thing to the next, okay? Substitution property oftentimes gets confused with the transitive property. And really, I mean, you could almost use them interchangeably, but the substitution property is basically if A equals B, you can replace B with A in any expression, or vice versa, okay? So you can replace something with an equivalent value, all right? And then our distributive property, remember, if you have something on the outside of parentheses, you multiply it in. So you distribute that multiplication, whether it's addition or subtraction inside there, okay? For example, if I look at something like this, let's pretend for a moment that we were going to solve this thing, all right? So we're going to solve this thing for x. We just have to justify each step. So we're going to do it the same way we would normally do it, all right? We're just going to justify each step. And if you were approaching this by going to solve this thing, the first thing you probably look at is say, okay, FED, fed is a straight angle, so that's 180 degrees. So these are supplementary angles. You'd probably start here and just say, hey, this guy right here, x plus the 2x plus 30, when I add those two things together, it equals 180 degrees, okay? And here's the thing. It's hard to justify that step because that's not really what's given. The thing about proofs is typically our brain jumps in about halfway through, but we have to say, how did we get there, all right? So I'm going to backtrack a couple steps before this, and I'm going to say, okay, well, how did we get there? We know those add up to 180 because I realized that FEC and CED were supplementary. So that would be the kind of the step before that. So I'm kind of working backwards to start. We wouldn't normally do it this way, but angle FEC and angle, well, actually, I should go one step further. What I'm doing is the measure of these guys added together. Equals 180. And I did that because I knew that angle FEC and angle CED were supplementary. Okay? And so I'm just kind of working backwards. Like my brain worked too quickly and got to that this plus this equals 180 too fast. But now the question, how do I know they're supplementary? Well, I know they're supplementary because FED is a straight angle. A really easy way to say that is to say that FEC and CED are a linear pair. See, they're two angles that are adjacent, and that's a nice succinct way of saying it. Say angle FEC and angle CED are a linear pair. See, now I kind of have this foundation built to justify each step. Let me scoot this thing down. There we go. So now I've kind of created some space. Let's start talking about this thing. I know they're a linear pair because, frankly, it gave me that they were a linear pair. It showed me on the picture that they were a linear pair. So when we justify that step, we just say that was given to us. All right, that's what we started with. All right, and then I said that those are supplementary because, remember, we had a special postulate that said if we have a linear pair, it's supplementary. And you don't have to state the name of the postulate. You'll never have to do that. Just describe it. Just say linear pairs are supplementary, okay? And you can abbreviate as long as I understand what you're talking about. And then right here, saying the measure of this plus the measure of it, that's the definition of a supplementary angle. That's what being a supplementary angle means. It means that they add up to 180. And now we're to that step where we said, okay, this guy plus this guy equals this guy. And if you don't realize what that step is, I replaced the measure of angle FEC with the value that it was listed as being. This is the substitution property. Okay? See, now I can continue to solve this thing. And see, you're probably looking at that going, oh, man, that's a ton of work. But again, your brain already knew all of that stuff. It was just a matter of saying what steps it was individually. Your brain jumps right to this plus this equals 180, but you knew that because they were supplementary, all right? And you knew they were supplementary because it was a linear pair. You just have to state that now. That's the big difference, okay? And again, we normally wouldn't start halfway through this thing. Normally, we're going to start with that linear pair thing, but your brain's not used to doing that yet, okay? So we jumped in where your brain would start, and then we backtracked and said, how did we get there, okay? So, but that's kind of what's going to happen when we start doing formal proofs here, all right? So now from here, I'm just going to combine like terms. And that wasn't really a property that was listed up there. We're just doing math, all right? And so you could say what you did here was addition. You could just write addition down because you know what addition is. Or a nice generic way to say it is I always like to just say simplify. All right, you just simplified. You did what elementary school kids do, and you did some operations, all right? And now from here, I would subtract the 30 from each side. I'm going to do that in my head, subtract the 30. But the fact of the matter is I still subtracted 30 from each side, so I did the subtraction property of equality. Okay, subtraction prop of equals. And now I'm going to divide each side by 3. I'm not actually going to write it, but when I divide each side by 3, I get a 50. Still, the justification is the division property of equality. And again, the subtraction and the division, you could do addition and multiplication. That would be fine. Some books won't even list the subtraction property of equality as a thing, all right, because it's covered by addition. Same thing with division, all right? And maybe subtraction, I should have put a T in there as part of my abbreviation so it doesn't look like substitution, all right? And so here's the thing. We already knew how to do this. Every one of you could have solved this thing, but justifying the steps becomes a little bit meticulous. It's that idea of minutia, looking for those little pieces, all right? And yes, your brain jumps in halfway through this thing. We have to retrain ourselves to say, okay, what was the actual starting point, okay? So now let's talk about properties of congruence. These are all the same properties, essentially, as we had before, but instead of using equal sign, we have congruence instead, all right? So the same properties we had with equals, we have with congruent for some of them, and we can apply that to segments or angles or what have you, all right? So again, I'm going to breeze through these pretty quickly. Feel free to pause if you need it. The reflexive properties, something is congruent to itself, all right? And again, congruence is used when we're talking about shapes, when we're talking about an actual object, all right, instead of values. The symmetric property, once again, if I have something is congruent to something, so segment AB is congruent to segment CD, I can switch it and say segment CD is congruent to segment AB. All right, it's the same thing. We can flip around the congruence sign, and we're fine. The transitive property, if AB is congruent, segment AB is congruent to segment BC, and segment BC is congruent to segment CD, then segment AB is congruent to segment CD. It's the same thing as before, but instead of equals and kind of bridging that gap, it's congruent and bridging that gap. And we can do it with line segments. We could do it with angles. All right. We can do it with actual polynomials, but we haven't learned that yet. The substitution property, if segment AB is congruent to segment BC, then segment BC can be replaced by segment AB in any kind of expression or situation. All right, and it's the same thing with angles. If two things are congruent, I can substitute in and out. All right. So now let's get to formal proofs. All right. A proof is basically a convincing argument that uses deductive reasoning, and that's what we did in that previous example. We used deductive reasoning alongside of how we would solve the equation to justify. All right, so it wasn't just doing that piece of solving the thing, it was justifying each step. That's deductive reasoning, okay? We're getting from one step to the next step. Because of this, I can say this. Because of this, I can say this. Because of this, I can say this, all right? And we're typically going to do this in a two-column proof style, and it's kind of like what we did in that previous example where I put my statements, in other words, what I am doing, on one side, and then I put the justification, the reason, the property, all right, what have you, on the other side. For example, if you look at something like this, it says, given that the measure of angle 1 equals the measure of angle 2, I want to prove that the measure of angle AEC is equal to the measure of angle DEB, the measure of angle DEB, all right? So, typically when I do these, I always start with the same thing. I start with what I was given. And I always label the steps just to keep them kind of consistent here so I can see which ones match up with which. So I'm going to say step 1, these are equal. And I know that because the problem told me that. And when something is being told to you, just say given. All right? It was given to me. I didn't have to do anything. I don't have to justify that. The problem said so. All right? So now we just kind of think about, all right, how are we going to do this? And in your mind, you're probably already looking at this going, well, I can tell that these things are the same. I just, how do I say that? All right? And you're probably looking at going, well, if 1 is the same and 2 is the same, well, that angle in the middle is the same thing. So if I have that 2 and that angle in the middle and I have 1 in that angle in the middle, then yeah, it's got to be the same because the pieces that they're made up of are the same. So kind of think about what you're talking about. If you're talking about combining those pieces, you're talking about the angle addition postulate, okay? So something like this, you could maybe jump right into this and say, well, the measure of angle 1 plus the measure of angle BEC, Beck, equals the measure of angle AEC. Okay? And so if you're looking at something like that, okay, yeah, that's true. And along those same lines, and I can include in the same step because it's the same justification, I could say that the measure of angle 2 plus the measure of angle Beck again equals the measure of angle, let's see here, it's BED, bed, or DEB, sorry. Let's do DEB since that's the way it's listed in the problem. Again, that's just the angle addition postulate. Oh, nice way to abbreviate angle, just use our symbol. Angle, add. And you can say postulate if you want, all right? Again, if you're not sure, just describe it. Say, hey, you know, little angles add up to the whole angle. It's angle addition, okay? And now from here, think about what you can say, all right? You know that measure of angle 1 equals the measure of angle 2, right? So, if you kind of think about that for a second, that's kind of like this. Couldn't I replace, in that first example, couldn't I replace that? Instead of saying angle 1 there, couldn't I say angle 2? And so when you look at that, I took that first kind of equation in step 2, that measure of angle 1 plus measure of angle Beck equals measure of angle AEC, but I replaced angle 1 with angle 2. Why am I allowed to do that? Well, because look at step 1. Step 1 said they're the same. I substituted it in. See, that's substitution. But now from here, check out what I have. I have the measure of angle 2 plus the measure of angle Beck equals the measure of angle Deb. But I have the measure of angle 2 plus the measure of angle Beck equals the measure of angle AEC. So I have the same thing equals that. Think about it in a different order. And here's the thing. You could switch one of these around to make it reflexive, but you don't have to do that. Think of it about like reading this guy backwards and just say, hey, the measure of angle Deb equals measure of angle 2 plus measure of angle Beck, and then measure of angle 2 plus measure of angle Beck equals measure of angle AEC. I'm there. The difficulty is maybe you're looking at it going, I'm not sure how to state which property it is. Wow, that is a funny looking M. Let me try again. And hopefully, if you kind of read one of those backwards, hopefully you see what property is. That's the transitive property. See, this guy equals that thing. That same thing equals the next thing. So the first thing equals the last thing. And again, it's kind of tough to go through this. It takes a lot of practice. This is a little bit of an art form. When you think about, doing a proof, it's almost like you're trying to fit one of the middle pieces into a puzzle. All right? If you've ever done a puzzle before, you don't start with the middle pieces. You can't just slap one down in the middle and say, that one goes there, I'm sure of it. The only way to know that that piece goes there is to start with an end piece or a corner piece, all right? And you have to work your way out to that middle piece to show that it goes there. That's what we're doing. We're trying to fill in all those little puzzle pieces that connect it to that anchored corner piece. You always start with the corners, right? And it's the same thing here. That's difficult because we know why this works, and we know that these are equal. But it's about justifying those little steps, filling in each little puzzle pieces. Because if one of those pieces is missing, we can't make it to that end result. Okay? Let's try another one. If I look at something like this guy. And so, again, when we set this up, we just do statements and reasons. And I just use an S and an R typically. And I draw almost like a table. And step one, I'm going to say, okay, here's what I have. Here's what I know. I know that the measure of angle 2 equals 90 degrees. And that BD is a line this time. It says so. Okay? And I know that because the problem said so. That's given. All right, I always start with the givens. So now I look at what I have, and it's okay. I want to prove that angle 1 and angle 3 are complementary. And so as you're looking at this thing, you should be going, okay, well, 2 is 90 degrees. BAD is a straight angle, so that's 180. Okay, so yeah, if that's 180 and I take away angle 2, that takes away 90 degrees. I'm left with 90 degrees. So 1 and 3 have to be 90 degrees. But start to think about how you came up with that. You started with the fact that BAD is 180 degrees. So maybe you want to say something like this. Well, BD is a line, right? So that means if you called it angle BAD, or maybe you could go right to, we'll do this. We'll say angle BAD is a straight angle. And we know that because, well, that's the definition of a straight angle, is that it kind of forms a line here, okay? And that it equals 180 degrees. So let's see, and we'll include that right in the same step since I'm using the same justification that I'm talking about the definition of a straight angle. And I'm not going to be super picky about some of this stuff, but so right here, that's the definition of a straight angle. That's what it means. Okay? So now I know that that whole thing is 180 degrees. Now I can say, hey, you know what? The measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. And you could probably tell me how I know that. The whole thing's 180 degrees. The little pieces add up to 180 degrees. It's my angle addition postulate. And now from here, I can say, well, wait a minute. I can replace that 2, right? Angle 2 was 90 degrees. So let me replace it. And if I replaced it with something that it was equal to, that's just substitution. And now from here, I just simplify this. I solve like I'm solving an equation. I would subtract that 90 from each side, right? Again, I'm not actually going to show the subtraction. You can if you want to, kind of in an in-between step. Most of us are probably good enough at solving equations. We can do that part in our heads. So I subtract the 90 from each side. And even though I didn't literally show minus 90 on each side, I know what the justification is. I know what I did was subtract 90 from each side. So I'm going to say that's the subtraction property of equality. And that's it. Like, I'm almost there. That plus that equals 90 degrees. Now, here's the thing. Students will tend to stop there. The question didn't ask me to prove that they add up to 90. It said prove that they're complementary. You're probably going, well, you're kind of splitting hairs there, Mr. Jansen. Well, yeah, but there's that little, that idea of minutia. We're one puzzle piece away. The fact that they add up to 90 degrees tells me that these are what kind of angles? Complementary angles. So now I can say angle 1 and angle 3 are complementary. And I know that because that's what complementary angles are, all right? And anytime you're looking at something going, well, that's just what that thing is, that means you're using a definition. That's the definition of complementary angles. Okay? So there's my proof. And, the other thing is this. Not every proof has only one way that you can do it. Especially as we get into more and more complicated ones, there are going to be multiple ways that you can do each of these things. Okay? If I look at something like this guy, it says X is the midpoint of segment WY. Y is the midpoint of segment XZ. Prove that segment WX is congruent to segment YZ. And the first thing I might do over here is I might say, X is the midpoint, so these are equal. Okay? And then Y is the midpoint of XZ, so these are equal. I already have one dash there, so that also has a dash. And right away, I'm starting to see that, well, I can see that those are congruent, but think about how I came up with that, okay? So let's backtrack a little bit. And see, as I mark it, that should be a clue as to how we're going to approach this in terms of the two-column proof. So step 1. X is the midpoint, capital M, of, WY. Reading is hard sometimes. Y is the midpoint of XZ. And we were told that. It said it right there in the problems. That's given. So now think about what I did when I was looking at that picture and I started to mark things. The first thing I did was say, hey, those two pieces are congruent because, X is the midpoint. So think about that for a second. You'd say, oh, well, I did this. I said WX is congruent. I marked it this way to XY. And I knew that because that's what being a midpoint means. Then I immediately said the same thing. So that's the definition of the midpoint. Whoops, I forgot my little 2. Okay? Then I immediately went, well, hey, X, Y, and YZ are congruent because once again, Y is the midpoint. I don't even have to do a separate step. I can use that right here. I can use the same justification. Anytime you can use the same justification, I'm fine with you using it in the same step. See, those are congruent for the same reason. That's the definition of the midpoint. Now, I want to show that, and when I marked this on there, it was really obvious. I went, okay, these are congruent because X is the midpoint. then I went, okay, this guy and this guy are congruent because that's the midpoint. Now I'm looking at going, wait a minute, I have the same number of dashes through each of those things. I know that those are congruent. Guess what? That's the next step right here is we say, hey, I figured it out. Wx is congruent to yz. Oh my goodness, my computer is going really slow. Yeah, these congruent symbols don't even look like congruent symbols. Sorry, I have to fix them. I can't live with this. Oh, beautiful. Look at I did it. But now what's the justification here? Look at the previous two steps. Wx goes to xy, xy goes to yz, so Wx goes to yz. Hopefully you can see it. That's the transitive property. Okay? And here's the thing. We did some pretty complex problems today. In terms of proofs, if you could handle this last one or something like this one, you're in pretty good shape for right now, okay? We want to build to some of those more complicated examples. And yeah, I did some of those with you today. But again, the idea here is to say, okay, what do I know? And then what else does that tell me about this thing, okay? And so we want to take it one little tiny step at a time and justify each step, all right? We're trying to figure out, hey, does this middle puzzle piece goes here? But we got to start with a corner and work our way over to that puzzle piece, okay?